The Colorado is the lifeblood of the region. It waters some of the country's fastest-growing cities, nourishes some of our most fertile fields, and powers $1.4 trillion in annual economic activity.
Beneath the dusty terrain of the American Southwest, the Colorado River has long carved its path, shaping canyons, nourishing ecosystems, and supporting tens of millions of people across 7 U.S. states and parts of Mexico. For centuries, its slow and steady power has been understood, respected, even feared, but never truly questioned. That changed dramatically when the United States Geological Survey (USGS) issued a startling red alert following a terrifying discovery beneath the Colorado riverbed. The announcement sent shockwaves across scientific communities and government agencies, halting ongoing research operations and mobilizing emergency geological teams overnight. Before we start, smash the like and subscribe buttons for more updates. The alarm was triggered after a series of unusual seismic readings and magnetic anomalies were detected near a remote stretch of the river between the Grand Canyon and Lake Powell. What started as a routine geophysical survey intended to map sediment layers for erosion studies quickly evolved into a high-stakes investigation. Subsurface imaging tools began picking up bizarre readings, densities that didn't align with any known rock formations in the region, coupled with sudden shifts in subterranean pressure. The data hinted at an active structure below the riverbed, not previously recorded in any geological assessments, prompting the USGS to conduct deeper, more invasive scans. What they found stunned them. Deep beneath the bed of the Colorado River, embedded in the ancient rock layers, lay a vast pressurized cavity, anomalous in both shape and intensity. The cavity wasn't just a hollowed-out void like a typical cave. It was a sealed geologic formation filled with a volatile mixture of superheated gases, mineral-rich fluids, and unstable rock. More concerning still, the cavity appeared to be expanding. The size of the formation, its orientation, and its volatile composition led experts to label it a high-risk subsurface geologic anomaly, one capable of triggering significant seismic or hydrogeological disruption if disturbed. Initial models suggested that the formation had been growing silently for thousands of years, its presence hidden beneath the vast layers of silt and sandstone. But only recently had the structure begun to shift, likely accelerated by years of drought, upstream damming, and increased groundwater extraction. These human factors might have altered underground pressures just enough to destabilize the long-dormant structure, creating new fault lines and exposing the potential for eruption, not of magma, but of extreme geologic force capable of displacing massive sections of the riverbed. The implications of this discovery are staggering. The Colorado River is a lifeline in the arid West. Its waters feed sprawling cities like Las Vegas, Phoenix, and Los Angeles, irrigate vast agricultural lands, and generate electricity through hydroelectric dams like Hoover and Glen Canyon. A disruption beneath its bed could result in a catastrophic shift in water flow, erosion on an unprecedented scale, or even the partial collapse of riverbanks in affected regions. Should the cavity breach the surface or collapse internally, the shockwave could destabilize entire sections of the river's infrastructure, including dams and pipelines. More chilling was the discovery of tectonic stress points clustered around the formation. Advanced geosensors showed that the surrounding crust was under active strain, with microfractures developing in branching patterns. The USGS has long maintained stress maps of the western United States, but this discovery marked a deviation from known tectonic behavior. The formation wasn't just sitting quietly, it was actively influencing its environment. These signs pointed toward a potential chain reaction. If even a portion of the structure ruptured under current pressure, it could set off a domino effect, initiating rock slides, triggering minor earthquakes, and possibly altering groundwater tables across hundreds of miles. Adding complexity to the situation, satellite thermal imaging revealed elevated temperatures in concentrated areas above the cavity, suggesting the presence of geothermal activity previously undetected in the region. While the Southwest is not devoid of geothermal hotspots, the heat pattern beneath the Colorado River was unprecedented in scale and structure. This raised concerns among geophysicists that deep Earth processes, possibly involving a rising plume of molten material, could be slowly pushing upward, creating not just geologic instability, but reshaping the landscape from below. One of the most unsettling aspects of the anomaly was its potential for sudden transformation. Geological formations typically change over millennia, but the rate of data fluctuation from seismic monitors suggested something was happening in real time. Pressure changes, temperature shifts, and small tremors had all increased in frequency in the weeks leading up to the alert. It became clear that the anomaly was not merely a passive geological feature, it was an active system, and one with the potential to reach a critical tipping point. The USGS Red Alert wasn't issued lightly. Red alerts are the highest level of geological emergency, typically reserved for imminent volcanic eruptions, massive earthquakes, or severe landslides. To apply this level of urgency to a riverbed anomaly indicated the level of concern within the scientific community. Research vessels, drones, and autonomous underwater sensors were deployed immediately to gather more data. River traffic in the area was halted, and a temporary no-fly zone was instituted, while aerial surveys were conducted using specialized radar and LiDAR systems. Though no evacuation orders were issued, nearby communities were placed on high watch. Emergency response protocols were reviewed and reinforced. Local officials coordinated with the USGS and FEMA to develop contingency plans for a range of scenarios, from gradual seepage of hazardous materials to sudden structural collapse. Meanwhile, environmental scientists warned of possible contamination risks if the cavity released mineral-rich fluids into the river. Some of these fluids could be highly acidic or laden with heavy metals, potentially devastating downstream ecosystems and agricultural zones reliant on irrigation from the river. Equally troubling were the potential long-term hydrological effects. If the structure's collapse led to sediment displacement or changes in the river's bed gradient, it could permanently reroute portions of the river. This would affect water rights, treaty obligations, and dam operations throughout the Southwest. Legal battles over water allocations, already a source of tension among states, would likely explode into full-scale regional crises if the river's flow became unpredictable or diminished due to geological instability. Another layer of complexity emerged from the possibility that the cavity might intersect with ancient fault lines. The Southwest is laced with dormant and semi-active faults, many of which have been stable for centuries. If the anomaly's expansion triggered reactivation of these faults, it could lead to earthquakes in areas not typically prone to seismic activity. The interplay between rising pressure, tectonic movement, and human infrastructure could create a perfect storm of cascading failures. Bridges collapsing, pipelines rupturing, dams cracking under shifting loads. Geologists also raised alarms over the potential for induced seismicity. The phenomenon, often associated with activities like fracking and reservoir-induced earthquakes, involves human activity influencing tectonic behavior. In the case of the Colorado River, years of damming, diversions, and groundwater depletion may have subtly altered underground pressure balances. Now, those alterations could be acting as catalysts, speeding up the natural processes at play and pushing the subsurface formation toward instability faster than it might have moved on its own. Complicating the response effort was the sheer inaccessibility of the anomaly. Buried beneath a rugged landscape of cliffs and canyons, directly beneath the dynamic and constantly shifting river, direct drilling or excavation was deemed too dangerous and potentially catastrophic. Scientists were limited to indirect data gathering, remote sensing, sonic imaging, and electromagnetic resonance techniques. This created significant uncertainty in modeling, as every new data point introduced fresh variables that had to be accounted for in real time. Public awareness of the discovery spread quickly, fueled by the red alert and heightened media attention. Despite government efforts to manage the message, speculation ran rampant. Social media lit up with theories ranging from ancient supervolcanoes to government cover-ups. The real story, however, needed no embellishment. The science itself was dramatic enough. A hidden structure buried beneath one of the most vital waterways in the western United States was showing signs of imminent transformation. An underground system alive with pressure, heat, and motion. The discovery also raised philosophical and existential questions about humanity's relationship with nature. For all the dams, diversions, and engineered solutions that have been built around the Colorado River, the Earth still holds surprises, powerful ones, hidden deep beneath the surface. The river, once thought to be tamed, was now shown to be resting atop something wild, ancient, and not fully understood. It was a sobering reminder that despite technological advancement, humanity remains at the mercy of forces it cannot fully predict or control. Amid the scientific urgency, political ramifications began to surface. Senators and governors demanded briefings. Federal agencies scrambled to assess infrastructure risk. International water treaties with Mexico came under scrutiny, as any disruption to flow rates would ripple across national borders. Emergency funding bills were proposed to expedite research, while debates flared over whether enough had been done to monitor subsurface conditions in critical water zones across the country. Meanwhile, indigenous communities, many of whom have long warned of the spiritual and ecological consequences of over-extraction from the river, viewed the event through a different lens. Elders from Navajo, Hopi, and Ute communities spoke of ancient warnings passed down for generations, tales of the land's deep memory and the need for balance. In their view, the Earth was responding to imbalance. While their insights were largely dismissed by mainstream science, some researchers found resonance in the notion that what lay beneath the surface was not just geological, but a reckoning of sorts. The terrifying discovery beneath the Colorado River has upended assumptions, forcing a new reckoning with the unseen dynamics of Earth's crust. It has ignited an unprecedented level of collaboration between geologists, hydrologists, climatologists, and emergency planners. While the full implications of the formation are still being studied, one truth is already undeniable. What lies beneath the surface, whether rock, water, or pressure, is far more volatile than anyone previously imagined. As research continues and pressure monitors tick upward with each passing day, the region holds its breath. The red alert stands not just as a warning but as a symbol of Earth's unresolved power, a reminder that beneath the river that gives life to the desert, something ancient and dangerous is waking up. In the days following the red alert, teams of scientists, engineers, and specialists from multiple federal and state agencies converged on the region. The priority was to map the anomaly in greater resolution and determine, if possible, the limits of the growing subsurface cavity. Sophisticated gravity sensors, magnetotelluric arrays, and deep penetration radar systems were deployed in phases to sweep the surrounding land and riverbed in a grid formation. As new data poured in, the true scale of the structure began to take shape, and it was even more vast and complex than first imagined. The cavity wasn't a single uniform space, but a sprawling labyrinthine network of chambers, fractures, and vertical conduits stretching several miles in multiple directions. These channels appeared to be connected by a system of voids, likely formed through a combination of geochemical dissolution and tectonic shearing. The pressure readings from within some of the deeper pockets were so extreme they exceeded the threshold of earlier seismic simulations. That meant a collapse in one zone could trigger chain failures in adjacent sections, much like a mine shaft caving in one level at a time, each with increasing force. Crucially, these chambers were not filled with just inert gas or water. Spectrographic readings hinted at a unique chemical composition, a mix of carbon dioxide, methane, hydrogen sulfide, and volatile hydrocarbon compounds, all under enormous pressure. Such a mixture, if vented rapidly, would not only be toxic but could be flammable or even explosive under the right conditions. This gave rise to a new concern: a subsurface chemical eruption. Unlike a volcanic event, which might offer visual warning signs, this type of eruption could be silent and sudden, with gases forced upward along cracks and faults, emerging explosively from the riverbed or nearby cliffs with no time to prepare. The deeper geological implications of such a structure could not be overstated. It suggested the presence of an active geodynamic system beneath the river, possibly tied to a previously unmapped hotspot or ancient subduction scar. If this were true, it would revise the region's entire tectonic profile. For decades, geologists have believed the southwestern U.S. to be geologically stable compared to the volatile Pacific Rim. This discovery, however, pointed to a hidden system of vertical heat plumes and horizontal stress lines running directly beneath one of the most densely managed river systems in the world. Attention turned to the origin of the anomaly. While the current condition of the cavity was clearly dangerous, understanding its genesis could reveal what might happen next. Some theories pointed to deep mantle upwellings, columns of hot, buoyant material rising slowly through the Earth's layers, creating zones of weakness in the crust. These upwellings could remain dormant for millennia before reactivating under shifting tectonic conditions. Others speculated that a long-forgotten meteorite impact might have fractured the bedrock ages ago, forming a subsurface fracture zone now reawakening due to climate-related stress and groundwater withdrawal. Remote analysis wasn't enough. Autonomous boreholes were authorized, self-guiding drilling units capable of descending into the Earth while transmitting real-time data back to surface stations. These robotic probes, engineered to withstand high heat and corrosive conditions, began boring into strategic locations around the periphery of the cavity. One probe detected a shocking thermal gradient shift within only 300 feet of penetration, suggesting a heat source far closer to the surface than anticipated. Another recorded sudden changes in acoustic resonance, as if the walls of the cavity were in motion, expanding and contracting, subtly breathing like a living organism. While the scientific community scrambled to understand the phenomenon, the implications for infrastructure grew more urgent. Engineers assessed the region's dams, aqueducts, and power stations, simulating what might happen if pressure from beneath caused vertical displacement of the ground. The results were unsettling. Many of these critical structures were built on assumptions of geologic stability. A sudden upheaval of even a few feet in the wrong area could undermine dam foundations, buckle spillways, or fracture buried pipelines. And because the river supplies drinking water to more than 40 million people, even temporary disruption could ripple across municipal systems for weeks, possibly months. Another point of concern involved aquifers, specifically the interface between the underground cavity and the Colorado Plateau's complex web of groundwater reserves. If the cavity breached into one or more of these aquifers, it could contaminate the water table with gases or chemical-laced fluids. Worse, the structural integrity of the aquifers themselves could be compromised. Water could suddenly drain into newly opened fissures, causing sinkholes or depleting wells that communities rely on. The interplay between surface water and groundwater, already a subject of intensive study, now took on a new urgency in light of the threat beneath. Federal researchers brought in specialists from geothermal and deep earth physics fields to assess the unknowns. Their focus was on identifying whether the growing pressure was a natural spike or a long-term escalation. Early models leaned toward a cyclical release of geological energy, but at far shorter intervals than expected. Instead of centurial events, the pressures and material movements suggested decadal or even subdecadal cycles, which would make the Colorado River Zone one of the most active geodynamic regions on the continent. What made this situation particularly dangerous was its invisibility. To the untrained eye, the river continued its timeless flow through the landscape. Tourists rafted down canyon rapids, hikers camped along cliff edges, fishermen cast lines at sunrise, and yet, hundreds of feet beneath them, forces capable of reshaping the entire southwest landscape were quietly amassing. If not for the red alert, the anomaly might have remained undetected until a disaster occurred. This revelation left many questioning how many other such hidden systems might exist beneath major water bodies, undetected and waiting for a trigger. Another unsettling angle began to emerge from geological analogs around the world. Certain regions like Lake Nyos in Cameroon and the Dead Sea Basin have recorded cases of limnic or geological eruptions, sudden releases of gas from underground or underwater that lead to suffocation, explosions, or massive environmental change. While the Colorado River situation was different in scale and context, the underlying principle remained the same. Trapped materials, if released rapidly, can be deadly even without accompanying earthquakes or lava flows. Government and civilian communication systems were quietly updated to accommodate new alert codes specific to subsurface gas threats. Emergency management agencies in Arizona, Utah, and Colorado began implementing drills for geological release events, a new category of natural hazard previously unheard of in the region. Local communities were advised on how to respond to the sudden appearance of ground fissures, unusual odors near the river, or strange animal behavior, all potential early indicators of pressure shifts below the surface. Meanwhile, ecological surveys were intensified to monitor possible biological responses to underground changes. Insects, small mammals, and migratory birds often react to subterranean shifts before humans detect them. In recent weeks, researchers had noted that certain bat colonies near the Grand Canyon had changed their flight patterns. Fish counts in some tributaries revealed sudden population drops, suggesting possible chemical shifts in the water. These indicators, while not conclusive, painted a picture of an ecosystem beginning to react to deep, unseen changes. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the USGS Red Alert at Colorado Riverbed? We want to hear from you. Thank you for watching, and see you next time.